This is a first in a series about Nyquist diagrams. We start by asking the question, what is a Nyquist diagram? So earlier videos in the series on Bode diagrams showed what frequency response was, and also showed how that information could be displayed, and in particular the Bode had one figure for gain information and one figure for phase information. In this video series we're going to consider how we might get the gain and phase information on a single figure. Later on we're going to ask why this is useful for feedback loop analysis and design. So we're going to begin with an engineering type definition or explanation of what is a Nyquist diagram. Some background first. So if you look at the videos in Bode diagrams, you will see that we defined what we meant by frequency response. So in essence, if you had a sinusoidal signal going into a system, G of S, then asymptotically you'll get a sinusoidal signal coming out. Now that's assuming that it's not divergent, obviously. And what you would notice is there's a difference in the amplitude of the output and the input, and there's a difference in the phase. So the differences in amplitude, or the multiplicative factor, was defined as the gain A, and that depended on the frequency of the input sinusoid omega, and similarly the phase shift phi of omega depends on the frequency omega. But we did show it was rather tedious to try and compute A and phi from time responses of this nature. So there was a shortcut, and this was the shortcut. If we knew what the transfer function was, G of S, then you could show that A of omega was given by this formula, the modulus of G of j omega, and the phase shift was given as the argument of G of j omega. So in summary, all you're doing is you're taking G of S, you're substituting S equal j omega, and then you end up with a complex number, and you're finding the modulus and the argument of the resulting complex number G of j omega. So that's a shortcut way to finding the frequency response of a system. Now, when we did Bode diagrams, we separated the gain and the phase information for the complex number G of omega. But we're not going to do that with Nyquist diagrams. We're going to take the complex number as it's given, and in other words, a Nyquist diagram is simply a plot of G of j omega in the complex plane, and here's the key thing, for all real values of omega. Now, usually we're going to focus on positive values of omega when we're doing our sketching, but in the long term you'll see a complete sketch also will include negative values of omega, but we won't go back to that probably for another 5 or 6 videos at least. So here's an example. What have we got? We've got G of S given here as 1 over S plus 1, and we therefore can write G of j omega equals 1 over j omega plus 1. And that's a complex number. And what we want to do is plot this complex number for different values of omega. So if now you look at the table, you'll see first we've said what's 1 plus j omega as we change the values of omega. And then we've said what's G of j omega by inverting it, and you'll see we've put all the numbers down here, so you can see. So now all I need to do is plot these numbers in the complex plane. So you'll notice I can do the easy one first, it's not in the table. If omega equals 0, I've got 1 over 1, and that is there. If omega's 0.1, you'll see I've got 0.99 times 1 minus 0.1j. So that's pretty much here. If omega's 0.5, I've got 0.8 minus 0.4j. So that's going to be there. If omega is 1, I've got 0.5 minus 0.5j. So that's there. If omega equals 2, I've got 0.2 minus 0.4j. So that's there. If omega is 10, I've got 0.01 minus 0.1j, so that's about there. And what you'll see is if I was to do all the intervening values of omega, you're going to get a sketch that does something like this. And the arrow is in the direction, alright, of increasing omega. So when you put arrows on these graphs, they're quite informative. They tell you omega is increasing if you follow this direction. So hopefully that's obvious. You'll see we had omega equals 0, omega equals 0.1, omega equals 0.5. So you'll see in the direction of the arrow, omega is increasing. So there's a simple example of a Nyquist diagram. Let's take another example then. So given g of s is 6 over s plus 1, s plus 3. So first of all, I substitute s equal j omega, and I end up with this 6 over j omega plus 1, j omega plus 3. Now, if I want to calculate that as a complex number, it's quite messy. So what I'm going to do is I'm going to use what I did in the Bode series and say, well, I happen to know straight off what the gain and the phase are. I can just write those down. And now I'm going to calculate the gain and phase at a number of different frequencies. So at omega equals 0, so if I do gain, then I'm going to have 2. At omega equals 1, I'm going to get 1.34. At omega equals 3, I'll get 0.45, and at omega equals 10, 0.06. Now I'm sure you can do this in your own time if you want to check I've not made a silly mistake. If I do the phase, omega equals 0, you get 0 degrees. At 1, minus 63 degrees. At 3, minus 116. And at 10, minus 157. And I can now turn this back into a complex number. And so what you'll get is just 2 for that. You'll get 0.6 minus 1.2j there, minus 0.2 minus 0.4j there, and minus 0.05 minus 0.02j there. So that's an example of simply saying, I've got g of s, or g of j omega, can I calculate the complex number for different values of omega? And now, I need to sketch those onto the plot. So at omega equals 0, we had 2. At omega equals 1, we had 0.6 minus 1.2j. So that's going to be about there. So if I write it down, 0.6 minus 1.2j. At omega equals 3, we had minus 0.2 minus 0.4j. So that's going to be about there. So there we've got minus 0.2 minus 0.4j. And then at omega equals 10, we had minus 0.05 minus 0.02j, and that's going to be quite difficult to plot. It'll be something like that. So if I do this sketch and was to fill in all the intervening values, which you can do if you like, you'll find the sketch does something along those lines. Okay? So that's another example of a Nyquist diagram for a transfer function g of s. So some conclusions. The frequency response g of j omega is a complex number, and thus can be plotted on an Argand diagram as omega takes all positive real values, and this is denoted a Nyquist diagram. However, as you've probably gathered, computing the real part of g of j omega and the imaginary part of g of j omega for several different frequencies and then plotting is tedious. You really don't want to be doing this. And so therefore we need a more efficient method, and we'll start introducing how you might do this in the next video.